Alright, today's experiment is synthesis of methyl orange. Alright, so methyl orange is an indicator. It will change colors at different pHs. Alright, and to make this we're going to take our sulfonylulic acid, we're going to add a base. So we're going to add some sodium hydroxide. And that is going to deprotonate the sulfonylic acid. So that is a very strong acid, very acidic hydrogen. When you take off that hydrogen, you see that you would have three resonance structures here for this complex. Now, we're not going to do anything with this benzene ring and the SO3, so I'm going to call that R. So I circled that, and that is what I'm going to call R. Alright, connected to an NH2. So this is going to be a primary amine reaction. So now I'm going to write that as RNH2. That is what that is indicating. It is just a shorthand so I don't have to write it many times on the board. So that is the first thing that happens. We're going to add our base to our sulfonylic acid, and we're going to get just a simple acid-base reaction. In another beaker, I'm going to take my sodium nitrite. That would be sodium nitrite. So that is a sodium nitrite. All right, so that is a soluble compound. We are going to add hydrochloric acid to our sodium nitrite in another beaker. And this is going to do an acid-base reaction. So initially it's going to take the H off of your HCl, and then it does that twice. And so we're going to do this same reaction twice. So there should be two HCl's and there should be two Cl minuses, because we are going to fully protonate our sodium nitrite. All right, and now we have our cation, and now this cation is going to react with, we're going to mix the two beakers now, our RNH2. This is the RNH2. Remember, the R indicates this compound. All right, and so the primary amine is going to then attack the protonated compound here. It's going to attack the it's going to attack the nitrogen. Electrons go to the more electronegative oxygen, and you have this complex that has a plus charge on the O, plus charge on the N, and a negative charge on the O. All right, and so the electrons come down and kick out the H2O, and you are left with this complex here. And now we're going to do a tautomerism. So a tautomerism, we're going to take off the H here and have a neutral compound, and then we're going to put that H on this oxygen. And so tautomerism is when you're moving an H plus from one position to another in the same molecule. All right, and so that was the product of the tautomerism. Once you have that, the electron pair of your nitrogen comes in, forms a nitrogen-nitrogen double bond. The electrons go to the more electronegative oxygen, and now you have this compound here. All right, and so this is just a resonance structure. This is not a reaction. It is a resonance structure. We're only moving pi electrons, and so the arrow for resonance is this arrow. All right, and so you have your double bond to nitrogen, and then your single bond to oxygen. So now we're going to do another tautomerism. We're going to take off the H on this nitrogen, and we're going to put that H on the O here. And so that is another tautomerism. Tautomerism is not resonance. If you are breaking a single bond, that is a reaction. If you are only making and breaking pi bonds, then that is a resonance structure. All right, so this is breaking a single bond. This is forming a single bond. Tautomerism is a reaction. It is not a resonance structure. All right, and so here, the electrons from the nitrogen come in and form a triple bond, and it kicks out the water. So again, this is not resonance because we are breaking a single bond. All right, and so then you get your diazonium cation. All right, and remember every time that the R means that you have a benzene ring, and paired to that is an SO3 minus. All right, so we have that in one beaker, and now we're going to then add our dimethyl aniline. All right, and so that is going to react with our diazonium salt by the electrons coming down, forming the double bond to the ring, pi bonds going there, and then this pi bond connecting to that nitrogen, and then the electrons going to the other nitrogen. So now we have a double bond for our nitrogens, and we went from aromatic to non-aromatic. We have an sp3 carbon in the ring there. All right, and so that is our product of that reaction, where we have our 4 bonds to nitrogen, and it is positive. All right, and so the Cl minus, which came from our HCl reaction, you can show the H just coming off. You can show Cl minus attacking it, whichever you prefer. I'm going to show the Cl minus taking that H, and then the electrons go to form back your benzene ring and your neutral nitrogen. And that is our product. That is the methyl orange. All right, so now with methyl orange, I put the R group back in. So here's the R. And so here's the R, and then I put in the R group in. That's the R group. And so I just rewrote the same methyl orange, except I put in the R group. So there is the actual structure of methyl orange. All right, and methyl orange is highly conjugated, and so you have many resonance forms. All right, and so here I'll show you a full conjugation where the nitrogen electrons go into the benzene ring, which then go out to the diazo, two nitrogens, and then you have that going into the other benzene ring, which then goes to an oxygen from the SO3. And so that the pi electrons are moving all over the place in this highly conjugated methyl orange compound. All right, so let's go make some methyl orange. All right, so I have, that's good. I have in my 2 beakers. All right, in this beaker, I have my 2.32 grams of sulfonilic acid, 20 mils of deionized water, 4 mils of 6 molar NaOH. All right, so I dissolved that, and then I added 0.93 grams of sodium nitrite, and then I cooled it, and then I added 8 mils of deionized water and 4 mils of 6 molar HCl. So that is what is in this beaker. In the other 250 beaker, I dissolved 1.5 mils of NN dimethyl aniline in 10 mils of deionized water and 4 mils of 6 molar HCl. And so now I'm going to mix the 2 solutions. All right, and so that's why I waited for you to see that. I don't know if you, hopefully that was in the camera well enough, that those 2 clear colorless solutions turned into orange, and this is our methyl orange. All right, and so we want to make sure that this is basic, and so we're going to add some NaOH and H2O. And so we're going to add some more water, and we're going to add some more 6 molar NaOH to make sure that this is basic. All right, and to confirm the basicity of this, we're going to take our stirring rod and our pH paper. And we're going to dab it and make sure it turns at least a green, if not a purple color. We want this to be very basic. And so I'm going to stir it up. I'm going to just get a little dab on here, and then I'm going to touch it, and it is a dark purple, blue, very basic solution. All right, so that is what we want. That is our basic solution. And so there is our methyl orange. And so we have made our methyl orange. We're going to heat this up a little bit. Heat it up for a little while over on the hot plate here. And while this is heating, I'm going to weigh out 5 grams of NaCl. Then we're going to add the 5 grams of NaCl, and then we're going to add an ice bath, and then we're going to collect our methyl orange by suction filtration. Alright, so that should be right at 5 grams. That. Perfect. 5 grams of NaCl. So that is our sodium chloride. Heat this up, make sure that it is fully reacted. So a colorful reaction. So we're going to then isolate it, and then we're going to do our indicator test and see what color methyl orange turns in acid, and see what color methyl orange turns in base. So we will have our acid-base colors. Phenolphthalein is the usual indicator that we use, but methyl orange is also used in some other titrations. All right, we're just going to bring this to a boil, and then we're going to take it off. So all right, I'm going to get some ice. Alright, so we are dissolving it all back in solution, and then we're going to precipitate it back out. Alright, so it's boiling. Alright, so now that it's at its boiling point, I'm turning the heater off. Let it boil for a little while. So I'm going to remove it from the heat. Add the NaCl. All right, now I'm going to put it in the ice bath. And the solid will precipitate. Okay, so we have solid forming immediately in there as it is cooling off. Alright, so then we just collect that solid by suction filtration. And then we're going to we're going to wash it with some cold water, so let's get another ice bath going. Some cold water. So we got quite a bit of solid in there that we're going to collect by filtration. We're going to wash it with some ice cold water. Then we're going to dissolve a few of these crystals in 10 mils of water. We're going to add some HCl and NaOH and check out the change in color. We'll do that in test tube. Ready? Find some test tubes. 2 test tubes. That's what I need. All right. Here's the NaOH. All right, so we're ready to do our suction filtration. Here, so this is our NN dimethyl aniline. This is the liquid. We use 1.5 mils of that. The sulfonilic acid is just a solid, looks similar to salt, and we use the 2.32 grams of that. We have our ice cold deionized water ready, waiting for the rinse. So need some more ice. That was all the ice melted. I want to make sure that this is precipitated out completely. So All right, so I'm going to get a little bit of that out. There, put some in here. All right, so there's definitely some methyl orange that has filtered through because methyl orange is soluble in water, as we can see here. The water turns this orange color. All right, so what I'm going to do here is I'm going to add a couple of drops of sodium hydroxide. And so you will see what color that methyl orange turns in base. I'll get this closer to the... All right, so this is NaOH in the dropper. And then I'm going to drop it in and see if there is a color change. Not much of a color change. All right, so the basic solution is this color. And so our methyl orange, we added a whole bunch of base, is already basic. And so it has not been neutralized. So this is the color that you get when it is basic. And you can see that it is the same color. So it did not change. So this is already the color in base. All right, so it's an indicator. So it should be a different color in acid. So let's add some HCl. All right, so now when we add the HCl, we should see a color change. So hopefully you see that it turned a darker red. All right, and so now you have, in acid, methyl orange is red. In base, methyl orange is orange. And so the reason why we use phenolphthalein and not methyl orange is because it's very difficult to see from one shade of an orange, a yellow orange, to a darker red. It's hard to get that precise point versus phenolphthalein where there's no color and then there is a color. It's much easier to see. But methyl orange is an indicator that is used, and most of the time when you're using methyl orange as an indicator, you have a test. So you have, okay, so this is, say this is the color you're looking for. So you would have this out, and as you're doing your titration, you kept matching the color to that, and then when it's that color, you know then it is time to stop. So unlike phenolphthalein where you don't need to do that. There's no color or there's color, and then you're done. All right, so here is our methyl orange. I will get a mass of methyl orange. And then you can calculate your yield. Everything is 1-to-1 for the calculations for your theoretical yield of your methyl orange. We are not going to get a melting point of this. We are just going to get a yield. So, turn it off. All right. So forming good suction. So you see the product is an orange solid. And it might still be kind of wet. So get mass. And that's all we need. All right, and the mass is 0.45 grams, 0.45 grams. So that is our, actually 0.45 grams. And that is the end for methyl orange.